All right, welcome. This is the fourth lesson, I guess, in the series that I've been kind of developing with this curve y equals x to the 2n. We looked at symmetric normal lines, looked at what's going on there. We had a similar value that we came up with here, but it turns out it's different for the maximal curvature, which is what we're looking at here. In the last video, I showed how to come up with the critical points for the curvature of a plane curve. So we looked at those values, and now we're going to apply that to this specific curve x to the 2n. So first we look at where are the critical points. So the critical points that we saw from the last time, the values that we'd be interested in, critical points are where this is true. Okay, so we just have to set that up, figure out what x values make that true, and then that will tell us the locations, the possible locations of the extrema. So first thing to note is that the bin occurs at 0, so right at 0, the minimum curvature, and I think it goes to 0 as you go off on either side. So the shapes of all these are pretty much the same, like a parabola, except the higher value of n, it gets very steep, very fast, and then it flattens out more at the origin as n increases. That's kind of what's going on. So to look for those critical points, we got to solve this. With this curve, we just got to take the derivatives. You can see it involves the first, second, and third derivative. So that's what we have here. So just using the power rule for each one, and then substituting them in. So what I did was compute each side by itself. So first this side, okay, if we evaluate this, 1 plus y prime squared, so 1 plus y prime's here, squared. If we square this, we get 4n squared, and if we square x to the 2n minus 1, we get x to the 4n minus 2. So that's what we get here. And then the third derivative, that's this. So we plug that in there. Okay. So we'll distribute this later on. But for the other side, for this side here, we got 3y prime, which is that, y double prime squared. So now we square this term. Okay. So then that becomes 4n squared. Where am I here? Right here. 4n squared. Okay, if we square this, 2n minus 1 squared, x to the 4n minus 4. Okay, and then when we simplify that, we got 3 times 2 times 4, so 24 n cubed, 2n minus 1 squared, and then the x's, when we combine those, we get x to the 6n minus 5. Okay, so we get those two, and these two have to be equal, and then we got to figure out what x value makes that true. So we set these two equal, and what I did was distribute this through. So we get this here, and that's equal to this. So I put that on that side. Okay. And then one nice thing that we can simplify is that we have this 2n minus 1 in each factor. So what I did was divide by it. So that goes away. So in this first term, you still have 2n minus 2, 2n minus 2, x to the 2n minus 3. In the next one, the 2 will reduce it to 4, n squared, and that'll go away, and then you just have 2n minus 2 left, x to the 6n minus 5. And that's equal to, divide that by 2, 12, cancel out an n, you get n squared, and then one factor of 2n minus 1 goes away. Okay, so then here we have like terms, so we can subtract and get that to one side. And then by factoring, so we get the 4n squared out, x to the 6n minus 5. Okay, and then inside here, So here's what simplifies. What you have left from this part right here is 3 times 2n minus 1 after you factor out the 4n squared. So then when you simplify that, you get 4n minus 1. Okay, I'll leave the link for the actual document, so I typed this stuff, and you could probably read it a little bit better than you can read it on the board here. But anyways, this is what it ends up being. So simplify that, and then you can divide through by 2, so there's a common factor of 2. So you can clean that up a little bit. You get n minus 1 over here, and then dividing by, as long as you're not dividing by 0. But if we assume back here, x is non-zero, at 0 you have, again, the graph flattens out, so you get minimal curvature there, so you already know that it's 0 at that point. So you can safely assume that x is non-zero down here. And then divide, so n minus 1 divided by 2n squared, 4n minus 1, the whole thing raised to the 1 over 4n minus 2 power. So this is a even root of a number. Okay, and you get plus or minus there because of the symmetry. So you're going to have a maximal point on either side. This doesn't show that it's an actual maximum. It just shows that if it does have any critical points, it's either 0 or one of these. Okay, is essentially what this shows. So the next thing would be to show that it really is a max at those points. Okay, but I think that's probably long enough for this one. So this is part of what I've been looking at. So I'll post some of the write-up of this, and it might make a little bit more sense. So anyways, I'll try to see if I can come up with to actually show that it really is a max. But I mean, it's clear from the geometry that, I mean, looking at the picture, that this would be a max. But to prove it, it involves a little bit more ingenuity to get into it. But anyways, those are the critical points, and that was really the main part of the part here. So okay, so we'll leave it at that for now. All right, thank you.